Thank you for having me here. This has given me an opportunity to sort of look back on some of the problems I used to work on a while ago. Sort of reminded of this story of this man who says, I talked to my father 10 years ago, and I was surprised how dumb he was. And I talked to him yesterday, and I was surprised how much he had learned in the last 10 years. I feel like an old man looking back on this area of data streams. So just to locate people, I'm sure you've heard this little puzzle before. Let me start with the by now classical puzzle. Okay. You have two players A and B, and there are numbers 1 through n. And what A does is show the numbers 1 through n in some permuted order to B, but leaves out one of the numbers. Shows everything, shows n minus 1 numbers, leaving out one of the numbers. And B's task is to find what was the number that was left out by A. Okay. Obviously, if B had a memory to sort of keep track of all the numbers that he's seen, it would be easy for him to figure out what was the number that was left out. But we're going to assume that B has a very small amount of memory. Okay. Can just remember a couple of numbers perhaps, but not all the numbers. Okay. And by now, there's a well-known puzzle, and the question is, how does B find the missing number? And there's a very simple solution. Just give me 1 minute. But this very simple solution says that B does not keep track of each of the numbers that is shown. B just keeps track of the sum of the numbers that's been shown. And since every number is shown only once, you know that the total sum of n numbers is n times n plus 1 over 2. And so if he keeps the running sum, then if he subtracts it out at the end of n minus 1 numbers, he would know what the missing number was, and that would be exact. Okay? So a very simple puzzle to show you that with small number of bits, sometimes you can solve the problem exactly. In this case, find the missing number exactly. Okay? If you're really interested in thinking about this puzzle more, you may want to generalize it and see what happens if A leaves out 2 of the numbers rather than 1 missing number, or more generally, what happens if A leaves out k numbers. Okay? Then the algorithms become more interesting. Okay? I want to give you a different puzzle, which is trying to take the same concept but trying to push it a little bit further. Okay? What if we had only one memory item or one word memory? Okay? So imagine that now Alice sees a bunch of items, one after another, and at every moment, Alice or A has to maintain the median of the items seen so far. Okay? And again, if Alice could keep all the items seen so far, then they can sort the items or find the median of items at every moment and return the correct answer. But here, we are going to assume that Alice can only maintain 1 word of memory. Maybe it'll just remember 1 number and nothing more than that. Okay? And the question is, can you still solve this problem of finding the median? Okay? If you think about it, median is a very complicated aggregate. Okay? And it's not as simple as average. So median is a complicated aggregate. You'll soon be able to prove that in the worst case, you cannot really exactly keep track of the median. And so you may want to sort of weaken the problem in order to make some progress. So one way to weaken the problem is to say that each of the numbers that Alice sees is generated independently randomly from some distribution. Okay? And what Alice does not know is the distribution. Okay? And again, these are numbers in some range, and they're being uniformly randomly generated. And you want to know if Alice can maintain 1 memory location and be able to estimate the median. Okay? It'll turn out that Alice cannot exactly cannot calculate the median correctly, but there's a very simple and cute algorithm for figuring out and estimate some approximation to median. Okay? What I like about this puzzle is that when you hear the puzzle, you think about what can Alice do given just 1 memory location, or so able to remember only 1 item. Okay? If you think about it, there's not much Alice can do. Okay? And the most natural thing for Alice to do is to say at every moment there's 1 number, which is the guessed median. And when you see the new number, more than your current number, then you increment your current estimate by 1. And if it's less than your current number, you decrement your current estimate by 1. Okay? So obviously there are issues like do you want to increment by 1 or some constant or some more intelligently and so on. But roughly the idea is that once you drift it to somewhere in the close enough to the median, then with constant probability, anytime you move away from that region of around the median, you'll always get pulled back to the region close enough to the median. Okay? So you have some sort of estimate of the median by just simply remembering nothing about the past, but just tracking the current median, our estimate, and what the new number that arrives in front of Alice. Okay? So you can try to generalize this method for what would you do if you want to keep track of not the median, but maybe quantiles and so on. Okay? And what I again like about this puzzle is that it's a very simple natural algorithm. You're going to do a little bit of hard work if you want to actually analyze it. And it tells you that some things are possible even with very limited amount of memory. Okay? Maybe not exact answers, some amount of approximations. Okay? These are not typically approximations. For this particular problem, you won't get approximation that is in the spirit of what we prove in theoretical computer science. But I'm happy with it. I think it's, I don't know if Al wrote this year, but no, I've been spending a lot of time with economists, so my theorems are not quite the same spirit as the theoretical computer science theorems. So I want to sort of start from here, this intuition that there are problems that you can solve with a very small amount of memory. And I want to give two basic primitives that in the last 10, 15 years this area has developed. And these are nice primitives that once you know them, you can apply them in a bunch of different ways to solve many problems. Okay? And I want to talk about sort of newer topics in this area. The first primitive I want to talk about is called the Countman sketch, and it tries to solve the following problem. Okay? What you have is a very large array of items 1 through n, n-sized array, and what you see are updates to the array. Okay? So you see either increments in position or a decrements in position, and you see a whole bunch of these updates. And these updates are the property that you never decrement the counter below 0, so they're always non-negative, these counters. And you want to keep track of these updates. And at every moment, you might be asked, what is the ith position of this array? Okay, so it's an indexing problem. In databases, we know that this is a key primitive for a lot of database accesses. Okay? And we also know how to solve the problem more or less from our undergraduate algorithms classes, that you can either declare a hash array, or you can do a sort of balanced tree, B trees, and so on, okay, and solve this problem. But all of those methods assume that you can store the entire array. Okay? Once you can store the entire array, for each item you can increment and decrement, and you can look up any item very quickly. Okay? And in the spirit of streaming, we are going to assume that we don't have the space to store the entire array. We're going to work with sublinear space, or in fact, logarithmic or polylogarithmic space. Okay? And this particular problem has a very simple solution. What you do is you don't keep the entire array, but you're going to use some hash functions, and you're going to take the array of the domain of size n and map it to a small number of counters using a hash function. And you're going to do this a few times using a few hash functions. Okay? And all our algorithms guarantees are going to have some approximation epsilon, a term epsilon, and they're also going to be probabilistically right. So there's going to be some probability of success or failure of delta. Okay? And these two parameters are going to tell us how many hash functions we use and how wide is each hash function. So in particular, what you do in the first is that when you see an item I, you hash it to a bucket, and the number of buckets would be something like 1 over epsilon. It will be proportional. It will depend on the epsilon approximation. And wherever it falls in the bucket, you increment the counter or decrement the counter depending on whatever the update was to the ith location. Okay? So, and you use a different hash function for different rows. So each I will update one of the buckets in each of the rows. And number of hash functions is going to be log 1 over delta, where delta is going to be going to determine the probability of success. Okay? So in other words, all you have is a two-dimensional array of counters, which we increment or decrement. For each update, we go to one count on each row given by the hash function, and we perform the operation of increment or decrement of that counter. And then when, and then when there's a query that what is fi, we know we can take I and hash in through each of the hash functions and go to each bucket. The bucket will hash into each of the rows. And whatever is the counter there, we return the minimum value of those counters. Okay? And that's our estimation procedure. Okay? So it's a simple algorithm, and what we can show about this data structure is that when there's a query for I, the estimate that we return will be at least always the correct answer. And that's one-sided guarantee. And then with probability at least 1 minus delta, it's going to be at most the correct value Fi, plus something that depends on sum of all the other items in there. Okay. So we're using a amount of memory that is proportional to 1 over epsilon and log 1 over delta. There's no n in this amount of space that we use. So it's a very small data structure for any large n. Therefore, we don't expect to get we don't expect to get the exact answer. We're going to get some approximations. And this claim tells you that the estimate that we return will be always the correct answer, but it's at most a correct answer plus epsilon times the sum of all the other values in the array. Okay. It's a very simple proof to realize this. If you look at any particular row and look at the ith item, it landed on some bucket, and look at what's the contribution of all the other items to this bucket. Okay. Well, it's the sum of all the other items divided by the number of buckets. And the number of buckets is 1 over epsilon, so this will be epsilon times the sum of all the items. Okay. There's a constant e there only for making sure that the calculations are precise. So the total volume divided by number of buckets would be the contribution of other items to the bucket where the ith item landed. And so now you want to ask, what's the probability that the estimate is larger than the quantity that we claimed? Well, it's the contribution of the ith item plus the contribution of the other items. So probability that exceeds this quantity would be some constant times the expected value. The expected value we already have is 1 over the number of buckets times the total volume. So if you do a little bit of calculation, you realize that for each hash function, you're going to have some sort of constant probability. You're going to have 1 over e kind of probability of this estimate exceeding this upper bound we have. And then since we return the minimum value, then we know that the only way we could be wrong in our estimate is if each one of the estimates from each one of the hash functions turned out to be above the estimate, above the claim. And then therefore, you can sort of multiply all the probabilities, and you have log 1 over delta exponent term coming in, so you have overall probability of delta. Okay. So this is a very simple argument that you see a lot in theoretical computer science. An easier way to understand it is think about just what happens in a single hash function, and then assume that we have sufficient number of hash functions that you can drive down the probability of error the way you want it. And then in a single hash function, you're going to be wrong because of contribution of other items, and that's just total volume divided by the number of buckets. And so it's a very simple argument that tells you that with a good probability, your estimate is at most this term that we claimed here. As I mentioned, the space we use is 1 over epsilon log 1 over delta. That's independent of n. And the time for update is log 1 over delta. Okay, so it's also independent of n. So it's worth looking at this result a little bit closely. If you want probability of success, reasonable 1 in 10, 1 in 100, you're going to use a few hash functions, 3, 5, 6. Those are no hash functions. That'll be the number of rows. And you want the approximation to be like 1 in 100, you're going to use a bucket size of about 100, 100 buckets. So altogether, you tend to use a few thousand buckets, a few thousand counters to get a reasonable estimate for these items that you care about. Okay? And this is good when the items you're trying to estimate are very large with respect to other items. The items you're trying to estimate are 1 in 100 of the total volume. Then you use about 1,000 bytes, and you're able to track this entire data. Okay? So it's a very useful data structure to have. In particular, there's a lot of work went into for the community to reach this data structure. A lot of previous results before this data structure use space 1 over epsilon squared, which is only a polynomial factor in theory, but in practice it turns out to be quite large. So if you want epsilon 1 in 1,000 or 1 in 100, then 1 over epsilon squared turns out to be hundreds of thousands, if not larger, and that'll be a difficult memory for the applications that we had in mind. So a quick observation is, can you do better than this in space? And I'm not going to go through the proof, but this is for people who are getting into the area. You might want to know that there's a very nice, simple technique for being able to show lower bounds in this world. And almost always they're based on communication complexity, and I'm giving a very simple proof here of a simple observation. Okay? So you start with the problem where Alice has an n-bit string, and Bob wants to determine the ith bit. But in the communication model, Bob doesn't get to go and tell Alice what bit he wants, Alice gets to go first, and she has to communicate some amount of information so that Bob can figure out the ith bit. Obviously, Alice does not know the ith bit, so one would imagine that Alice is going to have to communicate all the n bits for Bob to be able to figure out what was the ith bit. Okay? And this can be formalized that, I don't want to go into the history of this problem, but we know that you need at least n bits, or omega n bits, for the communication to work. Okay? So assuming that we know these results, now we can show that our problem of estimating each item needs at least 1 over epsilon space. Okay? It's a very simple reduction. What you do is, we're trying to estimate fi and attract the array f. So imagine you have some sort of another bit string array I, and every time there is a 1 in the bit string that Alice has, think of that as a 2 in the corresponding element of the big array. And every time there's a 0 in the bit string that Alice has in mind, think of it as a 0 in the f array as well, except that you add an extra term to the 0th item in the array. Okay? The 0th item is special. Okay? So it has this property that once you do this transformation, then you realize that if the string that Alice had in mind is 1 over 2 epsilon in size, then since we added 2 for every one of the bits in the string, the total volume or total sum of all the items in the f array would be 1 over epsilon. Okay? And now, if you had a method for estimating fi's very well, then in fact, if you had a method for estimating fi better than the bound that we had for the count-min sketch, then whenever there is a 0 in the initial array, it'll turn out to be 0. Our approximation will only add epsilon times the total volume, but the total volume is 1 over epsilon, so that only adds a +1 term at most to our fi. So anywhere between 0 and 1, if our estimate turned out to be between 0 and 1, you know that original bit was 0. And similarly, if the fi estimate turned out to be between 2 and 3, then you know that original bit was a 1. Okay? So in other words, you take the bit string and you think of it as this large array. Now, whatever transformations you've done has a property that if you could estimate f tilde fi with better than the accuracy bounds we claimed, then you will know the original bit string. Okay? Therefore, you know that the number of any data structure or the number of bits stored in the data structure has to be at least 1 over linear in the bit string size, and that gives you the 1 over epsilon space lower bound. Okay? Again, this is an almost straightforward kind of argument, but I'm trying to communicate the flavor that now many problems in this area will have a lower bound derived from some sort of a variation of indexing problem or generalizations of it, some sort of a gap Hamming problems, and so on. Okay. So I just want to point out that there's a lot of sketches out there. There are a lot of dimensionality reduction techniques there, and a lot of projection techniques, but they're not all same. Many of them tend to use 1 over epsilon square space for this problem. That's primarily because they tend to think about preserving L2 norm. And for this particular problem, you don't need to preserve the L2 norm for the indexing problem. So we are able to do with 1 over epsilon space. And a lot of algorithms use hashing, but in order to do this analysis carefully, to make sure that the space you use is logarithmic, you need to make sure that you know the seeds. You need to argue about the seed length of the hash functions. And we're going to use pairwise independent hash functions and argue that that's reasonable seed length as well. And the other argument that I hear people use when they approach a problem of this type is that, well, you're getting an approximation for an item, why not use sampling? Okay? And sampling is a very powerful technique, and it's sort of difficult to argue that sampling doesn't solve a problem. But here is a sort of a simple argument that sampling would be difficult. Okay? The basic observation here is that we're allowed to add and subtract things. And samples are easier to maintain when you add them. When you delete items, then you don't know how to go back and resample. You may have to go back and resample, which we don't have, which we cannot do in the streaming world. Okay? So a good way to understand this is to think of someone who inserts or adds 1 to a million items, and you're allowed to keep 1,000 memory data structure. So after having seen a million items, you have some representation of the million items, and it's not going to be exact. And then this person chooses to remove all but 4 of the items out of the million items. And eventually, you have a stream of only consists of 4 items, and you have 1,000 bytes as memory. And you would think that if you use a sampling procedure, then think about after having seen a million items, if you keep track of 1,000 items, there's very little probability that you would keep the 4 items that adversary is going to leave behind. Right? Your chance of hitting all the 4 items is going to be very small. But the sketches have the property that they're totally linear, so if you have a sketch, this countenance sketch for 1,000,000 items, and then if you remove no matter which of the items you removed, eventually the sketch would be exactly the sketch for the items that are left behind. So you'd have a sketch for 4 items using 1,000 bytes, and in fact you'll be able to recover each item explicitly, exactly. Okay? So the linearity is a powerful technique for us, property for us. So what could you do with this data structure? It turns out that you can solve a lot of problems once you have this data structure. Okay? I mean, a good analogy is to think of databases where once you have indexing, you can solve range queries, and you can solve lots of arbitrary subset queries and so on quite efficiently. So here, once you have this indexing data structure, you can ask questions like, well, let's assume that I keep tracking all the updates to this array F, and at some point I want to figure out what are the really large items. Well, I can go through each one of the items 1 through n and estimate them. And I need to make sure that all the n queries get reasonably good estimates. And once I do that, I'll find out all the items which are very large. Okay, so each index query tells you items which are large. I'll be able to find out all the items that are large. And this is called heavy hitters problem, which has been much studied in databases and data mining. You can do a little bit more. You can say that I don't want to look at all the items 1 through n and do the estimation procedure, which could be expensive. So then what you could do is you could sort of observe that in each bucket, if you want to only figure out the very large items, then this idea of hashing has a property that it will separate out the large items individually in each of the buckets. So I'm making a very powerful statement. You have to prove these things in some weak form. But if you take a bunch of items and throw them randomly into buckets, and if you had a small number of large items, chances are they'll be separated in the buckets. And in fact, they'll be separated in such a way that they'll be the majority in each bucket. And then a simple sort of log size decoding structure will figure out the identity of the item in each bucket. That's a majority. And it'll take extra log n time, because each one of the buckets you're going to do extra log n work. But that will give you a very nice simple result that says that you will be able to get think of initial function f as a signal. You'll get a k term or k non-zero entry sort of signal version of the problem, such that it'll be nearly the best k-term representation for the signal f, where the k-terms are individual non-zero items. You'll get a very good approximation to that. In other words, in fact, you should actually be able to get, if the original signal or original function f had only k non-zero items, your representation should actually be able to find all the k non-zero items. But it's possible that the original function had k very large items and a bunch of very, very small items. Then what you'll find out will be the k very large items, and have the property that your approximation would have the property that whatever you left behind will be a very small function, very small volume of the total signal. Okay? So you get a theorem of the type, which is a version of the compressed sensing result. Okay? So if I could replace all the L1 norms here by L2 norms, then that would be very similar to the compressed sensing result. So what we have done is that we've taken a very simple indexing data structure and done very simple queries. And you got a result which is the L1 version of a compressed sensing result, which has got a lot of applications, as we know. Okay? Now, I'm simplifying the story a little bit. You could look at different norms on the right and left hand side, and there's enormous theory around it. But I'd like to sort of point out this website that has done some interesting experiments with this L1 version and compare it to the L2 version, which is something that you hear a lot more in the literature. Yeah. So it turns out that this particular sketch has been used for solving the heavy hitters problem, as I mentioned, compressed sensing. It can be used for estimating inner products, join sizes, and it's found over last few years a lot of curious applications, okay, including natural language processing items, machine learning applications. There's a very cute application to password checking that got New York Times coverage. It's a very, very cute application. And it turns out that people are actually building, I worked on Gigascope as a system in AT&T, but it turns out that there are other systems like CMON and Sprint, Sawzall and Millwheel are from Google. And that actually have code for this. There are a large number of code libraries out there. Okay. I was very excited when Joe Hellerstein once sent me an email saying, "No, I have a question about count mean sketch implementation." So he has a nice implementation as well of this sketch. And there are hardware implementations of this now. And generally, it seems to find a lot of applications. It'll be difficult for me to argue that this is the best data structure to use in every application where it's being used. But on the other hand, I think that it's a simple data structure that a lot of people understand it, and find it easy to use them. And it's not that bad in most applications. Some of these applications, actually, I don't know how the sketch gets used. Machine learning, for example, they use it in very interesting ways with some hash kernels that I haven't quite figured it out. But Alex Smola is one of the experts in this topic if you want to follow up more on this. Okay. So I think Preston McAfee once told me that I should get really nervous if people in the audience start looking at the watch. But he said you should get really nervous if they start shaking the watch. I want to talk about one other primitive. And here again, you have a large array f1 through n. And you again see updates of increments and decrements to the items in this array. And again, we're going to assume that there are no negative items. Okay, just to begin with. Okay, I'm not sure there's a restriction for most of the results I talk about. Okay. And rather than solving the indexing problem, right now, what I focus on is trying to get a sample. Okay. And the sample should have the property that when I look at this array, there are a bunch of items which are 0 and a bunch of items which are non-zero. I don't really care how large the non-zero items are. I just want to return one of the non-zero items with each of the items in the non-zero items with equal probability. Okay. So I want to sample from the non-zero items, say uniformly. Okay. You could ask for more general properties than this. This is called a L0 sampling in my language. And there are things like LP sampling for different P norms. Over the last 10 years, there's been a lot of theory around the sampling, but this is a good enough sample for me to sort of do the argument I want to do here, which is, you see n items, and so there are increments and decrements. At any given moment, there are certain non-zero items, and you'll be asked to get a sample. And you want the sample to have the property that the non-zero items are sampled uniformly. Okay. Obviously, this data structure problem has a property that at any given moment, you could have a large number of items, and then everything gets removed, and you have a small number of items eventually. And so you should be able to adjust dynamically to the number of non-zero items there, and be able to keep track of them, and be able to return one of them, and undo all this in a small amount of space. Okay. There are a bunch of solutions for this. I'm not sure I got the bound right, but there are a bunch of solutions for this problem. And I'm not going to tell you the solutions. Instead, I want to tell you one way to apply this result. Okay. And that's for a graph problem. Okay. So we're going to use this to define something called a graph sketch. Okay. And the way we want to define this is that for each node of a graph, you're going to have a vector, which is indexed over all the other nodes. And we're going to set it to be 1 or minus 1 in some sort of an ordered way. Right? For ai, j is 1 if j is greater than I, and it's minus 1 if j is less than I. Okay? There's a particular reason for setting it to be 1 or minus 1 in this manner. Okay? So for any given graph, now we have n vectors, one corresponding to each one of the vertices of the graph. Now, if you look at this closely, you'll be able to realize that for any subset of the vertices, if you sum up all these vectors, then it has this curious property that you're basically capturing the edge set between the set S and the complement of the set S. Okay? So the support of the sum would have this property. Sorry?
Edges have not been used before.
And if it's an edge, right? If Aij is an edge.
Oh.
Ij is an edge, sorry. I'm sorry. So a particular edge a particular word, the reason for focusing on the support is that it's important to look at the support of this array sum, and that has this property. Okay? And then what we want to do, and I'm going to go a little bit quickly through this. Okay? What we want to do is we're going to now solve a problem like dynamic graph connectivity. So in other words, you have a graph, edges are being added and deleted, and you want to be able to answer the connected components of the graph at any given moment. Okay? This is a well-known classical problem with lots of history of trading off times for update times versus query times for connectivity and so on. I'm going to just give you one of the bounds in this space of results. Okay. So you have a dynamic graph problem where edges are being added and deleted. And at any given moment, you might be asked a query that says, is the graph connected? Okay. And what we're going to do is every time there's an addition of edges or deletion of an edge, we're going to track that on the vectors that we have in mind. Each word node has an associated vector. We're going to think of it as additions and subtractions to that vector. And in fact, what we're going to do is not maintain that vector. We're going to maintain the L0 sample or L0 sketch of that vector. Okay? We're going to maintain a data structure L0 sketch from which we'll be able to get a L0 sample. That is a sample from the non-zero items with equal probability. Okay? Now, then what you want to do is pretty much run the algorithm that we would imagine you want to run when you want to answer connectivity. Right? Just take every node, look at an outgoing edge from there, and then now you have a bunch of components. You can collapse them, and then repeat the process again. Okay? And eventually, when you'd have either, if the graph was connected, all the vertices would have collapsed, or there will be different connected components, and you'll have a representative from each connected component. Okay? So that's the algorithm you want to run. And the cute thing is to observe that first observation is, well, given a node, how do you find one of the edges coming out of it? Okay? Well, that's like, look at the vector associated with that node, and you want to pull out one of a sample, L0 sample from that vector, which will correspond to one of the edges, outgoing edges from that node. Okay? That's a simple observation. Second observation is that you have to collapse all these nodes, collapse the connected components. And the way you do is you look at all the vertices in the component and add up the vectors. Then when you add up the vectors, you'll have this property that now you have to, that'll correspond to collapsing the nodes of this connected component. Now you have to find an edge coming out of there. And that'll be the same thing as looking at the data structure that corresponds to some of these vectors and picking a L0 sample from that vector. Okay? So in other words, we think of an underlying vector, and we repeatedly have to add those vectors and be able to pull out L0 sample, that is an item of non-zero support from that vector. And we'll be able to do all of this by just keeping the L0 sketch of these vectors. Okay? So you simulate the same algorithm that we know we can do, except you'll do it with this data structure of samples. Okay? So this is a very nice algorithm that appeared in SOTA 2012. And very exciting because for a while we didn't have nice, interesting streaming results on graphs, and there was some on matching and so on. But this was really a nice step, and there's been a bunch of results in graph sketches since then. And I have this result cited by Valerie King, Capran, and Joy, because while it's the same problem. It's not, and the techniques are somewhat similar, but they don't actually phrase it in this manner. And but it's also a very, very, very nice result on dynamic graph connectivity. Okay. Let me then switch into topics. So far what I've done is talk about a count-min sketch and the L0 sketch and showed applications for each. The count-min sketch has applications to compressed sensing. The L0 sketch has applications to graph problems and streams. And I just want to now go through a bunch of little topics of related results. Okay? So instead of getting an estimate of each item, if in the array, you might want to know, as items get incremented and decremented, you might want to know the L2 norm or square of the L2 norm of the whole array. Okay? It turns out to be a very useful function to have, and if you hear about it for the first time, it's not clear that you think it's an interesting function, but it turns out it's very useful for many problems we solve in this area. Okay? And so it turns out that you can get an estimate for that using essentially a count-min sketch. Okay? In other words, you want to now have a bunch of extra counters, and rather than taking the min over each of the hash functions, you're going to do the min again, but for each one of the rows, you're going to do a slightly different estimator. You're not going to look at the item, the bucket where I fell into, but you're going to look at a couple of buckets and do the different squares. Okay. There are a couple of other ways to estimate this, but this is a simple estimator for the L2 norm squared. Okay. And you'll get 1 for each one of the hash functions. Again, you take the min. Okay. And there are some details, such as if you, there are some cases where there are medians involved, but I'm going to talk about simplest version to communicate the idea. So we have the same structure as a count-min sketch, except that we have a few more buckets. And we always think of the buckets in pairs and look at the difference and square them. And sum it over the entire bucket width and take the min over all the hash functions. And that gives you a 1 plus epsilon approximation to the L2 norm. Okay. Now, people who look at this and who have seen projections and random projection, Johnson-Dindon-Strauss kind of results, can see the connection. Typically, in the random projection, you have +1, -1 for each of the dimensions, and you choose it with some probability, and you project it that way. And we're simulating that by saying that we're always doing +1s for all the projections, except that we're subtracting out a couple of counters. And that has the effect of the same effect as having +1, -1s in the transforms. Okay. Now, you use about 1 over epsilon square space. The update time is very fast, and you get a 1 plus epsilon approximation to L2 norm. Okay. Well, what can you do with this? Okay. By the way, this is at least faster update time than any direct implementation of results, of small space results for estimating L2. So what can you do with it? It turns out you can do a lot of things with this data structure. But one good example is solving a classical least squares approximation problem. Right? The least square approximation problem, you're given a large matrix, and you're given a column vector, a large matrix A and a column vector B, and you want to find what's the x such that AX minus B is minimized in L2 norm. Okay? And it has a solution that has n d squared time going back to Gaussian times. And what you can observe is that if you don't work with A and B, but you work with T times A and T times B, where T is this transformation matrix given by this sketch I described before, then you have a much smaller size problem. You don't have an n times D problem, but you have a problem which is polynomial in size D. And in that space, if you solve the least squares approximation, you get a 1 plus epsilon approximation to the original problem. Okay. Now, you've got to be very careful. Do you get a 1 plus epsilon approximation in the error, or in the vector norm, or in, okay. So that all of the details you have to work through. But it's very clear that at least if you look at the error form, it should be quite easy to show that if you work with this transform matrices, then you get a 1 plus epsilon approximation to the L2 norm. And you can get the minimum error, a 1 plus epsilon approximation to the error. And now the running times will be polynomial in D after this transformation. Okay? That transformation takes time in D log D. So you have a pretty nice improvement in D squared results from a long time ago. Okay? Except that this is not an exact result. It gives you a 1 plus epsilon approximation. Okay? Now, a similar logic, I'm simplifying a lot of the math involved, but a similar logic can be used for a lot of linear algebraic problems, low rank matrix approximation problems, and classification problems in machine learning, and so on. And there's been a series of results in this area. And I'm just citing the most recent result, which looks at the results in an even finer way of looking at trying to use some sparseness of the matrix to get even more improved bounds. Okay. So in other words, you don't want ND log D. You want something that even depends on the structure of the matrix. And there are such results in this paper. Okay. And they're all more or less inspired by the same observation that once you can take a sketch structure like this one and map down the original matrix n times b matrix to something that is dimension D, a polynomial in D, then you can work on that matrix. Okay. And it's been very powerful in the linear algebra area. Okay. Here is another result. So, sort of when I was planning this talk, I reached out to a whole bunch of people in the community and asked them, what should I talk about? Okay. And I was actually surprised by the sense of pride in these results in the community. I mean, there have been a lot of good results in the last 10 years, and people have really a very good sense of pride about the achievements. And so they had several points that they thought I should mention to this audience. And one of them was that while we have been thinking about this model of small amount of space, polylog space, and trying to prove results which are approximate in this model, the techniques that we developed are presumably useful for a lot of other problems, which are maybe not even in this model. Okay, certainly the dynamic graph result is on a standard sequential model, and you still get some interesting results. So there was sense that the techniques that we have in this area go beyond and have other applications. And there are a bunch of examples, and I don't want to go through all of them, but I do want to mention one nice result that that's got a lot of attention recently, which is the problem of computing the discrete Fourier transform. I was told that there are a lot of scientists in the audience, so I'm sure that this function means a lot to a lot of you. Okay, signal processing relies very heavily on some version of Fourier transform. And we all know that the fast Fourier transform result, which is a classical n log n time algorithm. And there's been about 20 years of progress on this problem on aspects of special case or sort of parameterizations of this problem. And a nice result to hook onto this sort of stream of research is a paper I cite here, which says that if you're looking at a signal for which you're computing a Fourier transform, and the signal had k signals of size n, but it had only k non-zero Fourier components, then you can compute it very fast. You can find this transform or those coefficients in k log n time. So imagine the k is less than n, then you're doing it in significantly better than n log n time. Okay? And there's a version of the result you can apply even when the function doesn't have a k non-zero items, but maybe k large signals, and a few other components have some non-zero elements as well. There's a very generalized result, but this result is already interesting for me. Okay? It says that if you're dealing with a Fourier transform of signal, which has say, square root of n non-zero components, you can actually find it very fast, very nicely. Okay? The authors I mentioned here have done quite a lot of nice work on implementing these algorithms and comparing them, and I would encourage you to look at this if you're interested in Fourier transforms in general. Okay. Let me mention one other result that I found interesting. When you're dealing with streaming, you deal with small memory data structures, but as soon as you think about the data being on multiple sites, the small memory data structures become small communication data structures. Okay? You start focusing on communication of bits. And again, there's a lot of emphasis in sciences on learning, so I wanted to give you one result in this area that I find interesting. So here you have two parties, Alice and Bob, and they have their own data set. And they want to find a linear classifier on the union of the data set. Okay? Now, there's a particular way to quantify the error of, they're not going to get the optimal linear classifier, or one that has minimum error, but they're going to come up with an approximate linear classifier, and it's going to have some error with respect to the optimal, which is in this case classified in terms of number of points that are misclassified by this linear classifier. Okay? So once you have such a definition, what they show is that they have a log 1 over epsilon round communication protocol. So Alice and Bob talked for about log 1 over epsilon rounds, and each round has a very small number of bits, like constant number of bits. And at the end of it, they're going to have an epsilon error approximation to the linear classifier. Okay? In other words, it doesn't actually depend on the number of items, number of data points that each party has. They're still able to get an epsilon approximation to the global linear classifier by communicating about a constant amount of bits. Okay? In a few rounds, in fact, the rounds have to be very carefully done. You start communicating parts of the convex hull of the regions you have in order to make sure that the other party has enough information to proceed. So it's actually an adaptive protocol. And, but it's a very, very nice result. Okay? And it was, I think, independently obtained by two teams of people, and they have generalized this further. It's sort of, it's a beginning of, I think, a nice stream of research in this area. Okay? I want to talk a little bit about privacy. Okay? There's a beautiful notion of differential privacy, which the last few years has been in the literature, and I like it because it lets us do math without getting too caught up in the reality. Okay. And so there's a beautiful notion that says that I can develop algorithms and guarantee some notion of privacy. Okay. And there was a recent question that says, well, now assuming you have such a claim that you have a code that computes an answer to a query, and it's guaranteed to be private. Okay? So imagine you want to compute something like average salary of n people. So you can imagine the data structure keeps each person's name and their salary, computes the average, and then when it has to give an answer, it gives the answer with the correct noise added to it. so that the output is differentially private or has a privacy. But one of the questions that came up recently was, well, this is a great notion, but what happens if you claimed and you had such a software system, and if someone breached your software and looked at your memory that you have in your code when you claim to be private? Okay. Very nice question, and it combines privacy and security. And at least when I heard the question for the first time, I didn't know how to formulate this as a nice mathematical problem. Okay. And what some of the authors did, and I'm sorry I don't have the reference here on the slide, so they formulated this question in a very beautiful way. Okay. They said, well, if you know how differential privacy is formulated, it says that look at an input, and look at an input which is slightly different from that input, that differs on input of one of the persons, for example. And then these two inputs should have similar distribution of output, okay, for all yada, 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 but that's the notion of differential privacy. It's a very, very nice notion, as I mentioned. And the way the authors here formulate the notion of what happens when there's an internal state breach is that rather than look at the input, think of inputs comma the state of the memory of the program that deals with all this computation. This entire combination should be differentially private. In other words, if there was either a small change in the input or a small change in the internal state of the algorithm, then the output should still have a distribution which is similar to each other. Okay? So a very nice way to formulate this. Again, lends itself to nice math. And what we could show was that using the techniques of count, min, sketch, and all-zero sketches, we can get some of the pan-private algorithms. Okay. The reason I mentioned this is because if you think of the definition of pan-privacy, it doesn't actually have any restrictions on amount of space used by a data structure. It just wants to have some guarantee of privacy, no matter, assuming that the input and the state of the algorithm, if they're slightly different, the distribution should be similar. So in fact, you could use a polynomial large, exponential large space in order to get pan-privacy. But it turns out that the best algorithms that we have for pan-private algorithms for pan-privacy use polylog space, very small amount of space. Okay? So the streaming algorithms tend to have the pan-private property if used carefully, and that's something that was ahead of time not clear that that's the way it should be. Okay? And that's, I think, is an interesting connection here. Okay. Finally, I looked at the audience, and I know that Avi Vigdresson was going to be here, and a lot of other people, Shafi was going to be here. Okay. So I had to make sure that all roads lead to cryptography. Okay. And complexity theory, but I'm not there yet. Okay. So I recently came across a result. I haven't had time to read it in detail, but I thought the premise was interesting. Okay. At least enough to get started for some people here. Okay. So this is a paper, this is in the manuscript form, and it says that they want to have cryptography against polynomial adversaries, but the algorithm that they want to use is a streaming algorithm. Okay. And the result they have is not quite a streaming algorithm. It has two tapes. They're both read-write tapes, so it's not quite a polylog space. But they make only a few passes over them. Okay. And they're able to, under some reasonable assumptions, generate certain one-way functions and pseudo-random generators. It seemed like a reasonable starting point for something, which I can't really vouch for the quality of the result or the correctness of the result, but I thought I should mention it as something that I just heard about a week or two ago. Okay. And that gets me to a point where I want to say that, well, it's an easy place to look back. I did not mention many results. Okay. There's some very nice results on outsourced streaming computation that I wish I could have talked about. But these 1-hour talks are an opportunity to piss off everyone in the audience. But hopefully what I could communicate to you was that there are two simple data structures, the count, min, sketch, and L0 sampling. And they're useful tools to have in your bag. And you'll find that they're useful if you want to solve problems with small space, but even otherwise, they're often useful as a quick, simple way to derive algorithms which are sort of approximate, but easy to reason about. Okay. That's the way I found them to be useful. Sudipta Guha, who's worked a lot in this area, has given me several examples which I cannot reproduce without his help, of course. I don't have the gravitas of Sudipta. Several examples, including facility location problems, linear programming problems, where now he starts out thinking from a sort of streaming point of view, and that gives him a handle on sort of getting improved bounds in complicated problems like facility location problems. Okay. I think that's a great storyline. Okay? And what I try to do was sort of give you examples of a few topics where there's research and things that I thought would be interesting. Okay? I like the distributed learning model. I think there's a lot going to be done. It's sort of it's a nice connection of active learning, perceptrons, and sort of communication complexity there. I like this pan-Travis model, as I mentioned. Ahead of time, I would not have known this is the right way to formulate the problems. And I still don't have any argument why the best pan-private algorithms had to be small space algorithms. Okay? If you're trying to protect against somebody breaching your software and looking at your internal system, do you have to have a small amount of internal memory in order to be successful? It's not a priori clear to me. But I think it's a nice connection to explore. And I'm very excited to hear so many people have an exciting feeling about this area of data streams. You know, I'm constantly surprised by how these results are useful. But 2 weeks ago, I think, I got contacted by a company that said that they were implementing count mean sketch, and they wanted to have me come and visit them and talk to them about how to extend it. And I thought it was surprising. You know, I thought there could be a lot of other data structures that you could use. Or being a startup company, I thought they could buy a bunch of machines and do map reduce and solve these problems. But apparently, there's still some room for doing things with small memory and very fast, and it's very exciting. Okay. Thank you.
One question, could you, is there a holy grail problem in the streaming world, or one or two?
I think most people in the area would say that, would have said 2 years ago that some of the graph problems were the holy grail problems. I think we made some progress on them. But I still think there's a lot of room to solve graph algorithms in the streaming model. And I mean, I know it sounds like a boring thing, but actually it's more exciting than that. Okay? Roughly, the argument I would make is that while in math, mathematicians know graphs for a long time, computer scientists know graphs for some time, maybe not as long as some of the mathematicians, but the sort of applied world is discovering graph as a data structure only now. Okay? It's only in the last few years that Facebook graph is actually an interesting data set to attack these problems. And there are lots of problems on these graphs, which are massive graphs, in which we don't know how to solve them using even thousands of machines. So any reasonable attempt at approximating them, having fewer communication bits, would be great. And I think a lot of problems that are open. Cut problems, clustering problems, type. One of my favorite sort of area that's out there that hasn't been explored is that there's a model where you have multiple machines that each of which has a stream, and they all had to sort of talk to a central site and sort of continually do the computation. And so you're looking at communication complexity, but you're looking at sort of continual communication complexity. You're not computing a single function in one shot. You're computing a function sort of over time. Every time it has to be right or approximate, and you're looking at what is the cumulative amount of bits that you sent between multiple sites to a central site. Okay? There's some very nice connection between that and Stroppian-Wolf theorems in communication theory. And, so not as well explored as I think it should have been explored. Okay? And finally, the perinatal thing that I'm sure everybody talks about is there's large amount of connection between the small space data structures and sort of what can we do with the model like MapReduce. Okay? There are many, many variations of MapReduce model that come about, which trade off number of passes, number of rounds, amount of communication, and so on. And it would be nice to sort of tie these models together in an interesting way. Okay? And I think that would be something that's on most people's minds, okay, from a theoretical point of view. And I want to say one more thing from an applied point of view, which is I got interested in these problems because in early 2000, a bunch of us worked in AT&T, and these algorithms were needed in IP traffic analysis. And I felt like I was working on something that the world needed. I would argue that in the last 10 years, we haven't found other exciting applications of streaming systems. Okay. I think that we've produced very nice results, and I think they're very useful in a lot of problems, but we haven't had large-scale systems that work with streaming data, and I think that would be something I'd love to see the computer science community sort of find such applications. We've been talking to scientists, we've been talking to internet companies, and generally we're not succeeded in finding a great common streaming system that will apply to a large amount of applications.